I guess we're recording now. Okay, good afternoon, folks. Welcome to the Senior Physicist Group talk. Before we start, I'd like to make a couple of announcements. This will be the last time that we will be broadcasting here from the American Center for Physics.
You're broadcasting.
Next month in June, our talk will be from the, Physical Center in University of Maryland, part of the Physics Department of the University of Maryland. And Mike Brabansky will be our speaker. He will be talking about Michelson's early experiments in Potsdam, Germany. Oh. Okay, with that, let me start the meeting. Our talk today is Astronomy in Practice, Teaching Non-Science Astronomy Through Asteroid Observations. Our speaker is Dr. Melissa Hayes-Gehrke, born in Western Pennsylvania, where growing up you had plenty of room to look at the sky. You get an interest in astronomy. She got her bachelor's degree from MIT in physics, atmospheric, and planetary science. After that, she went across the Charles River and got her master's degree and PhD at Boston University. She came to Maryland in 2004 and started to teach astronomy. And I'll put an interjection. At that time, I was fortunate enough to take her course, and it was really a great course. So with that, let me continue. She now teaches a couple courses, observing and involved in asteroids and let's see, what else? She is now a principal lecturer in the Department of Astronomy and also director of undergraduate majors in the department. Okay, her talk today is again teaching non-science astronomy through asteroid observations. Basically, the students choose what asteroids to observe and observe them remotely via a telescope, determine their light curves, and from that analyze it to determine the rotation of the asteroids. Finally, they publish their results in the Minor Planet Bulletin. So it's a really hands-on course. So with that, let me turn the podium over to Dr. Melissa Hayes-Gehrke.
Okay, thank you. Thank you, Donald, for such a gracious introduction. And I'm going to start sharing my slides here. I just wanted to give it a moment for everybody to get on here and share the slides and go into the slideshow. So I think everybody should be able to see that now. All right, so thank you. So it's really great to be here today. And as Donald said, my topic here, the title is Astronomy in Practice, Teaching Non-Scientists Astronomy Through Asteroid Observations. And so first, I just want to kind of reiterate a couple things about myself. So here's me. Oh, wait a minute. The slide did not change. The slide changed for me. There it goes. It was just a little slow, but it didn't change on Zoom. All right, there we go. Yes. So I am at the University of Maryland Astronomy Department. I was one of the first principal lecturers at the University of Maryland. And over the time that I've been in the astronomy department, I've kind of gone up the ranks, and I'm now director of the undergraduate program for astronomy majors. Our major, our major is growing substantially. And we are up to 140 majors, which is actually puts us at about the top 10 in the United States for astronomy program. Wow. We're a very large program. We also teach a lot of non-major classes. I'm also one of the undergraduate advisors for our program, so just mention that.
How
So-
many do we have?
This talk today is going to be a little meta in the sense that I'm not just
17.
going to talk about science, but I'm also going to talk about kind of teaching and learning science. Because my time at the University of Maryland, I specialize in how people learn, especially things like science and astronomy, and what effective teaching techniques there are for them. And so I want to talk about that a little bit as well. So it's going to be a little bit of a different direction for the talk. So I want to talk about what I'm going to talk about here. So my course outline. So first, I'm going to talk about the University of Maryland Gen Ed program and what is scholarship and practice, which is a new term. So I'm going to explain that. And then we're going to talk about asteroids. So why are asteroids valuable to study? And then I'll talk about how I designed this course, Astro 315, that the students are taking to learn about asteroids. Then we'll look at some of the student results of asteroids that have been published, and we'll get some student reactions to the course. So what do the students think about their experience? So first, I'm going to talk about the general education program. All right, so University of Maryland Gen Ed program, and scholarship and practice, this weird term. So the University of Maryland General Education program ensures the students get a breadth of education. And this is a pretty typical sort of program. There's courses in fundamental studies that have writing, communication, math, and then they have to take distributive studies, which is where they get science, history, humanities. And that's where this new scholarship and practice course is considered part of the Gen Ed program. I'll talk about that more in a moment. Then there's a couple other types of courses that students have to take, big question courses and diversity courses. So I want to focus in on the scholarship and practice course. So when the University of Maryland put in their Gen Ed program about 15 years ago, they decided, well, yeah, we've got to have the breadth of courses, but the difficulty with a lot of courses that are Gen Ed courses is they're largely survey courses. So you go in and like if you do an intro to astronomy course, you get kind of all the facts about the solar system and the sun and stars and everything. And it's really interesting, but it's basically you're just looking through an encyclopedia almost of the different types of topics. You don't learn as much about the process of science. You don't learn as much about how did we actually learn all of these astronomical facts. So it's not very interactive in that sense. It's more of a survey type of course. And that tends to be what traditional general education courses are like. So scholarship and practice is trying to be something different. So scholarship and practice courses, the idea behind them is there's two main things there that should have authentic practice. So the Gen Ed website describes it as students engage in authentic work of a particular field of study. So they're going to learn some facts as they do that, but it's not like they're just going to sit there and take in information. They're supposed to be actually engaging in whatever it is that that field does. And then the second goal is a tangible goal, that the students learn and practice skills of critical evaluation and participate in the process of applying knowledge in the pursuit of a tangible goal. Now, this has to be written kind of broadly because obviously the University of Maryland has many different fields and majors and everything. So this has to be kind of broad. But if we think and put those two things together for astronomy, if you think about the science of astronomy, what is more authentic in astronomy than making observations and analyzing them to find a scientific result? I mean, that's really how astronomy got started. I mean, the very first things were just people looking up at the sky and realizing things like, the sky changes every 24 hours. We have that rotation period of the Earth, and they didn't realize what it was at first, but they figured it out. So we started out with observations. And so today we do it with a lot more instruments and scientific capability, but this is the really basic idea behind astronomy is that we're making observations, we analyze them to get a scientific result. And so I have a couple examples here of course, big examples of astronomers observing things and figuring out important results, but that's been throughout history, of course. And so that's something that when scholarship and practice was developed as a type of course, I was really excited about this idea that I don't want to do a survey course in astronomy. I want to get students actually engaged in some kind of observations and coming up with a scientific result. And so that's where this is heading. And so that's the type of scholarship and practice course we have. And I think that this is a really innovative and unique type of course that the University of Maryland has. It's one of kind of our draws for University of Maryland. So in 2013, I developed the course Astro 315, Astronomy in Practice, as a course in which students observe asteroids in order to determine their rotation periods as a way of truly understanding the science of astronomy. So in this course, they do the authentic practice of observing, data analysis, figuring out results, disseminating their results, and they're producing a tangible scientific result. So they have this tangible goal that's actually beneficial. Now, I'm going to go on and talk about, if I develop this class, first of all, why asteroids? Why rotation periods? Why am I focusing in on those things for this class? And so we'll get into that here. So to do this, we're going to talk a little bit about asteroids. So why are asteroids worth learning about? And so first, some general characteristics of asteroids. So you guys probably have heard of asteroids, so just be very quick on this. So asteroids are planetesimals left over from the solar system's formation. So they're kind of building blocks from the origin of the solar system. There are lots of asteroids out there. When I made these slides a week or so ago, there were almost 1.5 million asteroids that have been discovered, and over half of those have gotten numbers, which means we know their orbits very well. So there's lots of asteroids out there, and we're nowhere near finding them all yet. So there's lots of targets. And then asteroids in general are rocky. So they're made out of rocks and metals, mostly rocks. They're very low density. They have unusual shapes, as we're going to find out. And so they're interesting targets. Now, where are asteroids located? As you probably know, the main asteroid belt is in between the orbits of Mars and Jupiter. And if I use my cursor here to just kind of indicate things, you can see on here many, many blue dots, so many that they've kind of merged together here in the middle. Those blue dots are representing asteroids. So the main asteroid belt is in this big belt here. The red dots are planets. So we have Mercury, closest to the sun, Venus, Earth, Mars, and then Jupiter out here on the edge. So you can see Mars's orbit here and Jupiter's orbit. And so the main asteroid belt is in between those. So that's where most of the asteroids are. Also, the yellow dot is the sun, in case you hadn't guessed. All right. Now, there's asteroids in other places as well. You can see asteroids inside the orbit of Mars. Those are what we call near-Earth asteroids. There's fewer of those. There's also these asteroids that orbit in the same orbit as Jupiter, over here on the left and over here on the right with my cursor. And those are the Trojan asteroids. They're the Lagrange points of Jupiter's orbit between Jupiter and the sun. And so they orbit ahead of and behind Jupiter. So there's lots of asteroids, as I said. We know of almost 1.5 million of them. So there's lots of targets. They're very interesting in that there are a lot of different kind of characteristics of them. But this is their general locations.
So where the Earth is,
yes,
that's solid blue.
Yeah. Well, and I was just going to say,
how many do we have?
The scale here is deceptive because in order to see things on the graph, we have to make the dots too big.
Okay.
So the dots are way too big compared to the size and the distances here. Even if I dropped you off, if I put you in a spacesuit and I dropped you off in the middle of the asteroid belt out here where it looks really, really dense, I just dropped you off in a spacesuit and you looked around, you probably couldn't even see an asteroid. So they're small as well. And I was going to talk about sizes next. Okay. So there's a lot of empty space there. So yeah, it kind of looks like Earth should be getting pelted with asteroids, but no, it's not a big concern. It is a concern, but not a huge concern. Yeah.
Okay.
All right. Yes. Okay. So some more about asteroids. So I was going to talk about size. So this comes in here. Oh, my slide did not forward. Let's give it a moment. See if the slide decides to go forward for all of you like it did for me. So what I was going to say, and hopefully the slide will catch up, is small asteroids are much more numerous, there we go, than large asteroids. And so this is a log plot that shows on the x-axis down here the number of asteroids, and I've put in numbers that are bigger than the original legend. And then on the y-axis, we have the diameter in kilometers. So the largest asteroid that we know of is about 1,000 kilometers in diameter. It's actually slightly smaller, and that is Ceres, the first asteroid that was discovered. There's only one that big. And then kind of the next size range that they have here, down around like 500 kilometers approximately in diameter. There's 3 of those, so there's not very many. But when we get down into the smaller sizes of asteroids, so diameters of 100 kilometers down to 10 kilometers, down to 1 kilometers, there's many more. So thousands to millions of them.
How big was the asteroid that we landed a spacecraft on?
Well, which spacecraft?
Yeah.
Yeah, we've done it several times. I actually, hold your thought. I have a picture to show that.
Good.
Yes, to show that. And in fact, it might be my next slide. And it is, yes. But my next slide has not caught up yet. So on my next slide, what we have here, we have images from spacecraft who have visited asteroids, almost all of them. So if you talk about which ones have been visited by or landed on by spacecraft. So first of all, the Japanese Space Agency sent Hayabusa and Hayabusa 2, 2 separate spacecraft, and they visited Itokawa, which is this little guy up here. This is all on the same size scale. And then Hayabusa 2 visited Ryugu right here, okay? And then OSIRIS-REx, which is a US spacecraft, visited Bennu. At the time that this image was made, it was still in the future, but it has now visited Bennu and in fact brought back the samples. This doesn't have a couple asteroids that we visited with spacecraft. Donald Johanson, who was just visited by the Lucy spacecraft, and oh man, there's one more I'm blanking out on that has been visited by spacecraft that's not on here, but almost all of them are. So what you can see is that, first of all, they are pretty small. If you can read some of the sizes, the biggest one on here is Lutetia, and it's 130 kilometers across. All of these other ones are significantly smaller, and that's typical for asteroids. You can also see they're not spherical. Okay, the asteroids have very weird shapes. They're kind of lumpy. It looks like their origin, their debris from the formation of the solar system. So they're oddly shaped as well. Okay, so just want to show a little bit of an idea of what asteroids are, kind of why they're valuable to observe. And then finally, on my diagram, this very bottom row is not asteroids. It's actually comet nuclei that have been visited by spacecraft on the same scale, just to kind of give the example. All right. So let's go on and think more about asteroids in terms of rotation and rotation periods, because that's what the students are observing. And so why are we interested in that? Okay. So first of all, why would we study asteroids in general? I mean, first reason, you guys are all here because you're senior physicists. You have curiosity. So humans are curious about these things. Secondly, solar system formation. As I mentioned earlier, these objects come from the formation of the solar system. They really haven't been changed since then. So if we study them, we're learning about that process. And so that's useful. Third thing is impact hazards. As you guys pointed out, there are asteroids around the orbit of the Earth. It's possible that an asteroid could collide with the Earth in the future. So we need to know more about the characteristics of asteroids. So if we want to deflect them, we would have the opportunity to do that. And we'd have the best plan to do that. And I will put as an aside, a different class that I designed at the University of Maryland is called Collisions in Space, which is about the threat of asteroid impacts and what we might do if an asteroid is heading for the Earth. That's also a very popular class. I don't teach it as much anymore because I'm teaching this other class, but other faculty teach it. Yeah. And then the third thing, future exploration. Asteroids may be good sources of materials for future exploration and technology. So it's something that we're looking at in terms of, another place that humans might go in space or robotic exploration for materials. So now, how about, how are we learning about these asteroids? The difficult part about this is that they are what I call here lonely individual objects. Contrary to what the orbit diagram showed with like millions of them out there, they aren't very close together in reality. And so what that means is that it's hard to study them because we can't really study them as a group we have to study them essentially one by one. And so that makes it kind of tedious to do. And so that means you need a large workforce to do it. So students are good for that kind of thing. Secondly, if we think about the value of studying asteroids, and we have to do it one by one, we can think about this as an analogy with the US Census, which is one thing I like to do. So when we want to find out about the demographics of the United States, we go to door, basically, and we actually literally ask people about their families and themselves. And we do that for a significant number of households and people in the United States. And over that process, we build up a picture of what asteroids are like, what people are like in the United States. We can do a similar thing with asteroids. But just like with the US Census, we wouldn't go and knock on one door and say, okay, we've learned enough. That must be what the United States is like. We can't do that with asteroids either. We have to keep finding out more about them to build up that picture overall. So students can contribute to building the knowledge base about asteroids by observing individual characteristics of asteroids. And so this is something that, even though it's a tedious process, we have to do this one asteroid at a time. Over time, we do build up that picture and we learn more about asteroids, and students can contribute to that. So talking about rotation period, my slides are not keeping up yet here. Measuring an asteroid's rotation period is useful, as we will see on the next slide eventually when it decides to catch up with us. Here we go. Rotation periods of asteroids are often related to their size. Smaller asteroids in general rotate more quickly. There are exceptions, but that is kind of a rule of thumb to that. And that's partly because of conservation of angular momentum, the spin up or spin down for smaller things. And then it's also related to their structure. Rotation can be related to composition structure because fragile asteroids can't rotate as fast. They will literally spin themselves apart. And we believe that's a way that contact binaries may have been made for asteroids. So this is something that we can study then as rotation periods. Now, the graph that I have here, this is again a log plot. I want you to look at the x-axis on the top, rotation period in hours, because that's what we generally talk about the most when we talk about rotation period for asteroids. We talk about period rather than frequency. And so you can see this goes from 2 to 480 hours. And then the y-axis is just the number of asteroids. And these different lines are representing different survey programs and just the statistics from those different survey programs. So what you can see in general is that definitely more asteroids have shorter rotation periods than longer rotation periods. So you can see in this range from about 2 to 12 hours, there's really a lot of asteroids that rotate in that range. And then there's fewer as we go out to longer rotation periods. Now, that's probably a true characteristic of asteroids, that they tend to rotate faster. It's also a bit of an observational bias, because in order to find long period asteroids, you have to observe them for a really long time, and that's more intensive and less likely to be successful. People won't do that as much. So that's an observational bias as well. What's definitely not an observational bias is this cutoff. Whoops, excuse me, I just accidentally clicked on my screen. Is this cutoff at about, I accidentally clicked and I killed the slides. I apologize. Let me start the slides back up. I stopped sharing accidentally. All right, share that. Okay, are we back? Let's see. Hold on. Oh, not yet. I feel like I'm sharing. You guys are not seeing it though, are you?
Not yet.
Oh, there we go. Okay, it's just very slow. Okay. Yes, there we go. You can see, I won't touch the screen again. You can see that about below 2 hours, there are no asteroids that are rotating faster than a 2-hour rotation period. And that is essentially a structural barrier, that asteroids that are 100 meters and larger, they really can't rotate any faster than about 2-hour rotation period because they will fall apart. The few asteroids that we've seen with shorter rotation periods are literally fragments like a meter or 10 meters across. And we've generally seen those as they come into burn up in the Earth's atmosphere. So we see them only for a short time, but they can rotate more quickly. So students can measure rotation periods of asteroids. And that's what I want to talk about next, is how we do that. So an asteroid's light curve tells us about its shape and its rotation period. So what is a light curve? Well, first of all, most asteroids aren't spherical. We saw that in the spacecraft images, that asteroids are kind of lumpy and they're very irregularly shaped. So that means that as they rotate, we see a periodic change in their brightness. And I show that example on my top graph. So on the top graph, the y-axis is just time. The x-axis is just time. The y-axis is brightness. And you can see that if we have an asteroid shaped like an ellipsoid, if it rotates this way, you can see the rotation pole, that we will over time see the bigger side of the asteroid. It rotates, we see the smaller side, and then the bigger side, and then the smaller side, and so on. So we see the asteroid be brighter, dimmer, brighter, dimmer. And if we have an asteroid that's sort of an ellipsoid in shape like this, it's essentially got 4 sides to it, if you think about it, because we have the first big side, the first small side, then the second big side, the second small side, and then it's finished rotating once. So that means that typically when we look at the light curve of an asteroid, we're expecting 2 maxima and 2 minima for a full rotation, okay, for this elongated type of asteroid. Now, one of the things that's difficult about studying light curves and asteroid rotation is that we don't necessarily know our point of view looking at the asteroid. So asteroids' rotation poles are not necessarily perpendicular to the planes of their orbits. So we might not be seeing the asteroid like we are in the top graph, where we actually see big side, small side, big side, we see the rotation. We could be seeing it where we're looking at the rotation pole. And that's what I show in the bottom graph. So if we're looking at the rotation pole, as the asteroid rotates, we're not seeing any change in the cross-sectional size. So we're seeing the asteroid essentially staying at constant brightness. And then in that case, we can't learn anything about its shape and size or shape and rotation period because we're not really seeing any variation in the light curve. So if we observe an asteroid and we get a flat light curve, it could be that the asteroid is spherical, or it could be that we're seeing it pole on. Now, in most cases, we're probably seeing the pole somewhere in between these 2 examples. So there's some kind of tilt that we don't know necessarily what that is.
No, the axis is normally pointing in the same direction.
Yes.
So as the asteroid goes around the sun,
Yes.
that should change that.
That's absolutely correct. And that's one way that over time and many lots of observations, you can build up a picture of what directions the rotation pole pointed in. And then that gives you more information about its shape. It's extremely difficult to do because we have this problem with the sun being in the way for half of the year in terms of orbits, and it's a lot of intensive time to be observing. But it has been done for some asteroids. Yep, that's absolutely right. Okay, so now let's talk a little bit more about this. I want to elaborate on this light curve thing, and I have an example here. So an asteroid's specific shape affects how its light curve appears to us. Now, this animation showing the light curve in motion was created by one of the Asteroid 315 students this semester, Mark Wagger. He took this image from Hayabusa of asteroid Itokawa, and we have full views of it because Hayabusa orbited Itokawa. And it shows the light curve kind of in motion represented in relation to seeing the big side, small side as it's rotating. Now, the other thing that I want to show here is how we typically represent light curves for asteroids. So on the bottom graph, you can see the x-axis is labeled as phase, and the phase goes from 0 to 1. That's basically the fraction of the way that we are through the rotation period. So if this asteroid's rotation period was 10 hours, then the x-axis of 0 would be 0 hours, the start of the period, and 1 would equal 10 hours, the end of the period. And then it essentially wraps back around, and the light curve should repeat with the next rotation period. Okay, so we usually will show these graphs by phase, and that's what I'm going to be showing as we go on. And then on the y-axis, usually the brightness is labeled in the magnitude system that astronomers use, and sometimes it's differential magnitude. And I'm going to talk about differential magnitude in a moment. That's relative to a constant source. So as we observe an asteroid, the goal here would be to observe this asteroid, look at its light curve over time, and put together a phase plot like this that has a coherent shape for one rotation, and that's the rotation period of the asteroid. Now, of course, it's a lot more difficult than this, because imagine if this was a 10-hour rotation period, usually you're not going to be able to observe an asteroid for 10 hours straight. There's going to be weather, there's going to be sun, daylight, there's all kinds of problems. For longer periods, it's even harder. Shorter periods are a little bit easier. And so we do this over many nights, and then we can combine the observations by phase in order to put together a coherent light curve. And we'll see that as we go on. So now I'm going to jump to talking a little bit about the design of the course that the students have, and then we'll put together some of their results. So we have this goal now for the Astro 315 students to observe asteroids, make their light curves, create their light curves from the observations, and use that information to figure out the rotation period of the asteroid. And then as a bonus, the shape of the light curve can tell us a little bit about the shape of the asteroid. So we can get all of that information. So how do the students learn everything they need to know? So first of all, just point out, the slide is delaying again. What I'm going to say here we go. The students are not astronomy majors. So this is a non-major course. And they may never have taken an astronomy course or even necessarily a math course at the University of Maryland. And they're here in my class. So we have a big range of backgrounds. And I put together this word cloud that shows the majors of the students in the last 2 semesters that I taught this course. Bigger means that there is more students of those majors. So computer science is the most popular because it's the most popular major at the University of Maryland. We have like 4,000 computer science students, so a lot. And then you can see other popular majors: economics, engineering. Letters and sciences is basically an undeclared major, so they haven't decided on a major yet. Mathematics, information science, and then we get less common ones: philosophy, biology, journalism, art history, English history, real estate. That was like the one I didn't even know we had a real estate major, but yeah, so we get all kinds of majors. So this is one thing that I have to keep in mind with the course is these students come in and they might not have any background in astronomy. They probably know the word asteroid, but probably they learned about asteroids from Armageddon, the movie or something. And so, they don't necessarily know what those are. Yeah. All right. So the structure of the course is planned to teach the students what they need just in time to be able to use it, because we just don't have time to do it more ahead of time. So just in time. So talk about some of the planning here. So we start with motivating the project, understanding the purpose of why asteroids are important to learn about. And so it goes into a lot of the things we've talked about already. And then the next part is we have to get ready to observe the asteroid. But first we have to know what asteroids are we observing. The students get to choose the asteroids. So I put together a very curated list of possible asteroids to observe. And then the students choose the specific ones that their teams will be observing. But that means they have to, I hold them to account for understanding and figuring out, will their asteroid be visible at the times they're observing, the dates they're observing, the location on the Earth they will be observing from? Will the asteroid be a good target for that? So that means they have to learn things about the celestial sphere and celestial coordinates, and spherical geometry is hard, so that's difficult. In order to understand when asteroids are going to rise and set, they have to understand local sidereal time. And that's something that probably a lot of us would struggle with, is local sidereal time. It's a very different way of thinking about things. They have to learn the magnitude system. So they have to learn a lot of these concepts so they can choose asteroids. I, of course, will oversee that and make sure they're not making poor choices, but they're guiding them along on that. And then they have to learn how to observe the asteroids. So they have to learn about light, so just the electromagnetic spectrum and wavelength and frequency and all this good stuff. And then they have to learn how telescopes work. They're using reflecting telescopes. They have to learn how CCDs work, because that's how we take the images and we record them to be able to analyze them. And then we use a telescope system called iTelescope. So they have to learn the specifics of how to use iTelescope. And then after we've got the observations, they're going to have to actually analyze and interpret that. So they have to learn how to interpret light curves. So they have to understand asteroid characteristics and how light curves are created, what they are telling us. So we learn about that. They have to know how to analyze their images. So there's CCD calibration they have to do to remove noise sources. They have to do aperture and differential photometry, which I'll talk about a little bit. And then finally, we get to the end. They've done all the analysis, and the analysis always takes much, much longer than they think it's going to take, because science is hard. And this is a really important thing for them to learn, is that you don't just go through and bang, you've got an answer, but it's difficult. But when we get to the end, they write about their results. We publish our results in the Minor Planet Bulletin, which is the typical journal for these types of observations. So they have to learn about the format and style, and they actually write the papers. All right. So this is a really ambitious course. There's a lot to do, and we don't have any time to spare. So let's talk a little bit more about the plan. And I'm being told my internet connection is unstable. So my slide did not want to change, but let's see if I can do it now. All right. Okay, there we go. So the other thing that's different about the course
Rudy
is,
has a question.
oh, yes. Somebody has a question?
Rudy,
Yeah, go ahead, please. Mute.
Where are the telescopes? I think you're using the student observatory.
No, we are not. And I'm going to talk about where the telescopes are.
Okay,
Yeah, yeah. No, we use remote observing.
Oh,
Yeah.
okay, okay.
Oh, that's something. Who had the question? Rudy had a question?
No.
Nope. Okay. All right. So
we're not
I-
hearing you, Rudy.
Rudy,
Oh, okay.
your microphone's not on. Oh, neither is mine, so I can't tell.
Rudy, your microphone is not on.
I have it off so I don't get the echo.
Yeah,
Yeah.
right, Jerry, we can hear everything you say.
Oh, okay. You get it from the room.
Right. No, sorry, Rudy. We can't hear you. Go ahead.
Okay. Okay. So another interesting part of the course is that the organization of the course focuses on active learning. And one of the big things that I use is what I call a flipped classroom. So instead of lecturing, I don't generally lecture. We have videos that the students watch ahead of time that take in kind of concepts and facts and things. And they have quizzes to check on that. And then in class, we have activities, and the activities are all based on what they should have learned in the videos, and it gets them to practice what they're doing to cement their learning. So things like understanding celestial coordinates and magnitudes and light. If they're doing these activities in class, it helps them understand. Whereas most of them, if they're just listening to a lecture, they're not really going to take that in and be able to use it. They need the practice. And then the other thing that we have is we have a lot of teamwork. The students work in teams of 6. There are 2 teams per asteroid to share the work. And so they get a lot of skills with that as well, a lot of collaboration skills. We have a computer lab section that meets weekly for the students. And the students use that time to learn the software that they will be using to plan the observations and also analyze the images. And then they do all the data analysis as we get to the end of the semester. And then I have frequent status reports. And those are 4 reports that the teams give on their progress in the project. And one thing I hadn't mentioned, I realized before now, is the size of this course. There are 48 students in the course each semester. So we have 8 teams of 6. And there's 2 teams on each asteroid. So we study 4 asteroids each semester. So it is a lot of organization, both on my part and their part. And it's very intense. There's a lot to do. There's a lot going on at any one time. Okay. So the students used itelescope.net to remotely control telescopes in Utah and Australia. So I mentioned that there were 8 teams. Yes, 8 teams, and we study 4 asteroids. We do 2 asteroids from Utah and 2 asteroids from Australia. And as I said, we have 48 students. The logistics of getting 48 students to our campus observatory would be horrible, especially we want 20 nights of observing. Plus our weather is not good. And especially spring semester, we always have this spring semester. So it's really a no-go on that. The logistics are much easier, but a lot of organization for the remote telescope. And so you can see an image of one of the remote telescopes here that we use.
Now, you have to
Yeah.
somehow be a university teacher or a high school teacher or something to use that. You can't-
Actually, this you just pay for.
Okay,
So,
and how much?
It's a lot.
It's a lot, yeah.
Yes, so the students pay a $50 lab fee, which adds up to $2,400. That is not enough. It's half to a third of as much money as we need. iTelescope recently raised their rates. We were fortunate enough that the college and our department chipped in a little bit of extra money for that. We are going to be asking NASA Space Grant to help fund us in the future because of the increased rates for the usage.
Okay.
But we spent about $8,000 this semester on telescope time.
Okay, so it's not available for normal people probably.
Actually, there's lots of normal people. Most normal people don't want 160 hours.
Oh, okay.
Yeah.
So it depends how many hours.
Yes, and which telescopes.
Yes, okay.
Yeah, we went for pretty big telescopes. All right.
Can't do this through AAVSO?
No, they don't have the same kind of setup. That's something I'd be happy to talk about later with folks. Yeah. Okay. All right. So here is just a movie that another student in Astro 315 made. Jackson Nagy put together a movie of some of the observations of the asteroid 5295 Messiah moving compared to the stars on one of the nights of observations. Now I put the arrow there, so hopefully you can see the little thing moving. And I like this video because it does show the asteroid moving, but it also shows a couple other important things. First of all, asteroids are unremarkable to look at in images. They're just little dots of light, and they're not very bright dots of light because they're not very big and they're not very close to us. So they're not bright. So it is a challenge to observe them. And also, the second reason, so they look just like stars here. And then you can see that the video skips a little bit between when the asteroid's moving, it kind of jumps a little bit. That's because of clouds that close the telescope for a while and we open it back up. So, there's a little bit of a gap in there. So asteroids do move significantly compared to the stars, but over the length of a night, they're in our image here. And so we just have the set of images that we analyze. Okay. So let's talk about that analysis. So once we get a bunch of images like this, and we had many hundreds of images between all of our asteroids this semester, once we get all these images, we have to make light curves for the asteroids. That means a whole bunch of brightness measurements. Okay, so in order to measure the brightness of the asteroids, the students use a process called aperture photometry, and this is an extremely powerful method that pretty much anything you've ever read about the brightness measurements of is done by aperture photometry. So it's very powerful. The idea here is you have the object aperture, which on the image is in red, and the object aperture measures the brightness of, everything in it. That should be your object, your target, so the asteroid in this case. And it also measures the sky background brightness because you've always got some of that extra background in that aperture. So it's the object plus the background. And then we don't want the background brightness. We want to get rid of that somehow. The way we get rid of that is we use the sky annulus. Now the sky annulus is shown in green on the image and the inner annulus and the outer annulus. So the sky annulus is in between the inner and outer annuli. And so that is used to measure the average brightness of the sky background. And then we subtract that from our target aperture. And so that in principle will give us just the brightness of our object. So the asteroid in this case. So this is what we do step by step for every single image, hundreds of images. And it gets even better in terms of measuring this, because then we want to make sure that not only are we taking care of effects of the sky background and removing the brightness from the sky background, but we will also naturally have changes in the atmosphere as we observe. So the transparency, there might be a little bit of clouds coming in, the seeing, the kind of the turbulence in the atmosphere will be different, and that will change brightness measurements too. And we want to remove those effects.
I guess
yes.
differences in temperature will give you a bit of a wiggle too.
Yes, that's correct. Yeah. Another
So,
question?
so what the student actually gets from each of these is, and a photograph or a picture?
From the
I mean,
telescope?
And then they make the measurements of the brightness?
That's correct, yeah.
Locally?
Yes, yep.
Okay.
The students are doing that, yeah.
Okay.
Yeah, in our computer lab.
Okay.
Yes, yeah. So the way we take care of atmospheric effects is we use something called differential photometry. So we not only do aperture photometry on our target, the asteroid, but we also perform it on non-variable stars that are in the image around the asteroid. And those are used as a constant reference to determine the asteroid's brightness changes independent of atmospheric effects. Because what will happen is if the transparency of the sky changes or maybe some light clouds come through, everything in the image will get a little bit dimmer. And then the clouds go away and everything in the image gets a little bit brighter. But if we were just measuring the brightness of the aperture only, we would see that dimming and brightening as a change in the asteroid's brightness, but it's not. If we compare it to our constant objects, then we can remove that effect. And so I have here a screenshot from the software we use looking at the different brightnesses of comparison stars. We call these comp stars, comparison stars. And we can measure up to 15 comparison stars. So if you imagine we have 16 objects in hundreds of images that we're doing aperture photometry on, it is a lot of measurements. Fortunately, the software will automate a lot of this. And Rudy, I see you have your hand up. Do you have a separate question or was that from before? And can you turn your mic on? Maybe not. I don't see him moving. Okay. So what we end up with then is we end up with a list of differential magnitudes of the asteroid over time. And that's our light curve. So then we have to try to figure out what the rotation period is. And we do that by making the phase plots and getting them to line up into a coherent shape. So let me talk about that. Some of our results, because we're getting toward the end of our time here. So asteroid results. So what have the students found? So first I'm going to talk about our results from this semester that we just finished. We had our final exam on Monday. Okay, so from this semester, one of our 4 asteroids was 4163 Surema, and you can see its phase plot here. Remember that the x-axis is the phase, the y-axis is the brightness. And this is a main belt asteroid that's about 20 kilometers in diameter. The rotation period that we measured for it was 26.315 hours, plus or minus 0.025 hours. And you can see how it very nicely creates this nice sinusoidal curve, very similar to the example diagram that I had way back at the beginning of the talk. So this asteroid is probably a roughly ellipsoidal shape. It's elongated. This has a pretty high amplitude of the variation here. So it's got an ellipsoidal kind of shape. Now you see the light curve is not completely filled in. We have some gaps. That's because this rotation period is 26 hours. Imagine you go out every night at midnight and you want to measure this asteroid. You go out at midnight tonight and tomorrow and the next day and the next day. You are measuring almost exactly the same point of the light curve every night. And so it makes it very hard to get kind of full measurements of the whole light curve. We were fortunate that the students had collaborators that were located in Malta and Slovenia at different longitudes, and they contributed observations to this as well, and that helped us to get better coverage of the whole light curve. So this asteroid never had its light curve published before. It did have a tentative period that was published from Gaia photometry, from the Gaia spacecraft, but they do that en masse and they don't have light curves that they publish from it, and they don't really verify the period on it at all. Yeah, Donald.
The minimum there on the right is more than, so that what, different reflectivity?
Yes, so it can be different shapes, different reflectivities, and also things like craters and lumps on the asteroid.
Yeah.
Yes, yeah, exactly. All right, our second asteroid that we observed was 5295 Messiah, and this is also a main belt asteroid about 20 kilometers in diameter. Whoops. Sorry, my slide forwarded, but the next slide did not. The slide on the Zoom, there we go. It is not 20 kilometers in diameter, it's about 21 kilometers. It's a Hayes-Gehrke family asteroid, which is in the main belt. This has a much shorter rotation period, 4.13 hours plus or minus 0.01. And you can see it's got a gorgeous light curve, very nice sinusoidal kind of light curve. So it's also an elongated asteroid. This one's much easier to observe with only a 4-hour rotation period. We can almost see the whole thing in a night if we're lucky with good weather. So this was the first published rotation period and light curve for this asteroid. One thing that you might notice on each of these plots is in the upper right on this one, you can see that there's a bunch of list of numbers, a legend next to the points that are plotted from like the 80s up to the 90s. Those are all different dates on which the asteroid was observed. So you can see that it was observed on many, many nights in March and April this semester. And so that's what that's corresponding to. Now, these first two asteroids were our prettiest asteroids. The next two were harder to do. So this next asteroid, if my slides will forward, is called 3961 Arthur Cox. There we go. It's also a main belt asteroid. It's smaller than the previous ones. Look at the rotation period we found, 57 hours. Now, when you start to get to longer period asteroids, 57 hours becomes very difficult to observe. You also will notice that our data were noisier. We're not really sure why. We had some weather issues, but not really sure why the data were a lot noisier. That's why the error bars are a lot bigger. But you can see that for 57-ish hours, we have a pretty distinct light curve here with 2 maxima, 2 minima, like we would expect. This is the first published rotation period and light curve. And so we're happy with how this turned out. It was much more difficult than the other two.
With the lumps
Yes.
of data, then you fit the curve.
Yes, that's correct.
Okay, but the right curve doesn't bend like the.
Yeah, well, this is a fit with a Fourier series.
Yeah.
Yeah, sine curves. And so it's not just first order. I forget how many
It's
orders.
not
It's third
a
orders.
pure sine curve.
No, it's third order. So it's 3 sine curves added together.
It's
3 sine curves added together. It's third order. Yeah. And so that gives you these funny shapes. Yes. Now, our last asteroid we observed this semester was also a difficult one, 19774 2000 OS 51. Another main belt asteroid, about 51 hours for its period. And this light curve is a little funkier. That's the scientific term, funkier for this. We did not realize, so you might say, why are we picking hard asteroids to observe? Well, of course, the rotation period was unknown. We didn't know they would be hard to observe.
Yeah.
That's one of the challenges with science. You don't know how it's going to turn out. And that's one of the points to make to the students. You don't know how it's going to turn out. It turns out we discovered with some research at the end of the semester that there were prior astronomers that had observed it and they couldn't find a rotation period. So if we'd done that, that might have been a little bit of a warning. There was one person who had it as one of objects in his PhD thesis, and they found a rotation period with half the value, but that did not make sense at all for our data. So we're more confident in this longer period, but it is a little weird. Now, I want to show you kind of some of our greatest hits from Astro 315, since we've been doing this class for over 10 years. And I'm going to skip this because we are running out of time. So some of our greatest hits. 1852 Carpenter on the left has a rotation period of almost 30 hours that we discovered. And the thing I like about it is its funky light curve here, but it's got so much data overlapping over so many different nights that, yeah, that's what the asteroid's doing. It must have a very lumpy shape, a very kind of unusual shape. The asteroid on the right is one of the longest period asteroids that we've found, which is almost 90 hours, 1466 Mundelaria. And you can see again, though, the data fit the sine curves very well. It's quite repeatable. There are gaps, and we'd like to fill those in, but it's a pretty good case that this has that long period of almost 90 hours. A couple others here. 1856, whoops, if I switch here, it's going to go to 1856 Rosana, which looks very different from Carpenter. If we get the slides to switch, there we go. This is a shorter period asteroid, almost 6 hours. You can see it's got a really classic kind of sine curve shape. It's pretty high amplitude. So this is a nice, just ellipsoid type of asteroid. The one on the right is remarkable because of how short the rotation period is. So this one, we published a period of 2.24 hours, but we did not have a lot of data for it. It was confirmed later by other astronomers to be a period of about 2.1 hours. So we were pretty close. This is a very fast rotating asteroid for a main belt type of asteroid, which would be a substantial in size. It's a very fast rotator. Now, the last one I want to show you kind of from our greatest hits, this is our most famous asteroid that we observed in our very first semester of the course. So 3905 Doppler. It's got a period of almost 51 hours, but the remarkable thing about it is if you have seen any kind of light curves before, you will recognize this is an eclipsing binary. So just like eclipsing binary stars pass in front of each other and block some of their light, eclipsing binary asteroids do the same thing. When we chose this asteroid as a target, it was not known to be a binary and not known to be an eclipsing binary. So this actually got quite a bit of news. We had a electronic telegram, electronic these days, but telegram sent out to observers to kind of get a call to action to get more people to observe it. We got a nice story in the campus news about it that, you know, the students had discovered a rare eclipsing binary or double asteroid. And you can see the very nice light curve here showing the eclipses very distinctly. And then if you took out the eclipses, the spikes from the eclipses, you would still get a sinusoidal curve. And that is the combined light of the two asteroids when they're essentially next to each other, orbiting each other and not eclipsing. So they are still elongated and we're seeing different amounts of the cross-sectional area there. So that's the underlying curve.
But there is no bell. So you
I
can
know,
run
but
over.
I don't know. I don't want to run over too much if you guys don't want to. Question, yeah.
Yeah, there's some telescopes going up in the future
Yes,
for surveys, where they'll take a picture every night
yeah,
of the whole sky.
yeah.
Are the asteroids bright enough that you could actually use the data from that?
Yes. Yeah, that is actually, so when I mentioned previously that Gaia had observed the one asteroid, that's the same sort of situation with a survey and you catch all of these objects incidentally. Somebody has to go and put together all of those observations because, for example, if I back up my slide, if we look at Rosena here, which has a 6-hour rotation period, if you take a snapshot of that once a night, you are getting very sparse measurements of that asteroid. Now, in principle, if you've got hundreds or thousands of them over a series of nights, you can break them up and phase them together and put them together. It's a difficult task, but that's one thing that is definitely going to happen. Like you're thinking about the Vera Rubin telescope for one thing. Yeah, so that will definitely happen. And that's been done already with some of the current surveys. Okay. So I want to wrap up by talking about, summary. I forgot about my summary of the students. So far I've taught the class for 10 semesters. I've had almost 450 students in total. We've observed 43 asteroids and we publish one paper per asteroid. So the students have published 43 papers. So we're adding step by step, block by block to the knowledge of asteroids. And I have a photo here of some of my students from this semester. And I said, can I take your picture for the talk? And they're like, sure. So here they are working on Sorema, if you can see here. All right. Now, just a little bit of a summary. Student reaction. So how do students like Astro 315 and doing this? So I did do a nice survey about this and we got some good quotes here. So some of the quotes, I like best doing something real that contributes to real world knowledge. I felt like my work meant something. Another student, I liked how this course was tailored specifically for non-astronomy majors. I feel like Dr. Hayes-Gehrke made each topic super easy to understand. That is the idea. I fully enjoyed the lecture learning style and how hands-on the course was. And I enjoyed contributing to actual scientific research. Doing the observation sessions was fun and very rewarding. The amazement that they get when they take several images in a row and the asteroid moves is just, it's really neat to see. And then last quote here, getting to observe an asteroid and publish a paper about it will probably be one of the most memorable things I will have done. Yeah. And these are students, none of them are going into astronomy. So it's a really great experience for them. Yeah, yeah,
time period over which they're taken looked like 13 or 14 days that the actual data was.
yeah, yes.
So
Typically
you don't
it's
have
about
to
3
do a
weeks.
correction for the fact that the Earth is rotating.
No, over that short of a time, not really. But one of the things to notice, if I go back in my slides, well, the slides actually go back. Let's go back to this one, just because it's nice and big. If you notice at the top, under the headline Doppler there, it says JDO LTC, and then it has a bunch of numbers. That is the Julian date, and LTC stands for light time corrected. So the software that we use to analyze the observation dates each measurement at the time the light left the asteroid. So then it takes care of some of the things that you might be thinking about with the Earth's motion, the
Well,
asteroid's
I mean,
motion.
it's rotating, but the axis it's rotating about,
Oh,
we're seeing it
oh, yes,
differently
yes.
as we go along.
If
So,
we did it over a longer period of time, it'd be a bigger deal, but it's generally
right.
not.
I mean, if you
Yeah.
were to take data from Nancy Grace or something, you'd have to
Oh, yes,
account for
yes,
that.
that's definitely true.
For
Yes.
that fact that the Earth
Yes.
is rotating and you're seeing
So
it at
you would
different
have to
angles.
be careful that you would have observations that were in similar phase angles. Yeah. you would.
Right.
Yeah. The hard part about that is we don't know the rotation periods and the rotation poles for most of them. So that makes it very difficult. Yeah. Okay. So this was the end. I need to stop and ask if there are more questions, and I can certainly elaborate, but I don't want to go too over time. So thank you very much for inviting me.
Okay, there's no overtime.
Yeah, I know, but yes, people are expecting probably about an hour. So,
Well,
yeah.
if they're still here, they're still here.
If they're still here, they're still here. Great. I'm going to X out of my slides just so I can see more questions, and I can start them again if I need to, but what questions do folks have? Go ahead and unmute and ask.
I'm not sure we're getting any communications from
Rudy?
From anybody.
I don't know. Oh,
there we
we're
go.
hearing some people. Jay, yeah.
Yeah,
Okay.
a couple, well, sort of comments, really. One, as interesting one, there was one asteroid sometime this afternoon is passing within 1/3 of the distance between the moon and the Earth.
Yes. Yeah. That happened, yeah.
It's sometime this afternoon.
Yeah. That happens more often than you might think. Seriously, I mentioned that I created the other class on asteroid collision potential, and I learned a lot about that there's a bunch out there, and they pass by pretty closely pretty often. But they're so small.
This one's about the size of a bus.
Yes.
The other thing is, some of them might become interested in astronomy, and you can tell them about IOTA, which does asteroid work. That's their purpose.
Yes. Yep. Mm-hmm. Thank you. Ted,
Ted has a question.
So in terms of simulating real science, did you tell them about H-index so they can keep track of how influential their paper are?
No, I have not. Yeah.
For you, does this count toward your publication count for the department?
It does. However, my position is a teaching position. I am not expected to do research. So this is a bonus on top. Yeah.
Got it.
Yeah, yeah.
And you don't have them prepped to write grant proposals to do more.
I do not. The fortunate thing about minor planet bulletin papers is that if it's for a single asteroid, they're typically 1 to 2 pages in length, which is a very reasonable length for students to tackle. And tackle is a good word for what they do with it. Yeah.
One other question. You've got these teams of 6 students.
Yes.
How do you distinguish them in terms of grading?
That's a good and complicated question. And students ask the same thing. First of all, I will say my course syllabus is 20 pages long. I have a very detailed plan for the entire semester. There are a number of components to the course. So a lot of them are individual based. So there's like pre-lecture quizzes and some writing activities, et cetera, that are individual based. And then in terms of teamwork, they do those 4 status reports, but they rotate around on who is the primary author on each of them. And they get more weight for those in their grades, and the others are editors, they get less weight. There's other kinds of assignments where they're able to kind of trade off on that. They also submit 5 team evaluations throughout the semester on an online system where they give anonymous feedback about their teammates. And if teammates are rated very low, I can deduct from their scores. And I have done that. Yeah.
Very sophisticated.
Yes, it's definitely a big thing. In general, though, it's amazing how well the teams get along because they work pretty intensely together for the whole semester. And it is something that they get to know each other, and generally they're not hostile, at least to each other. I think they develop a fairly good kind of professional working relationship, which is something that I'm trying to get them to learn to do, because it's something they'll be doing in their careers, is working with other professionals and thinking about how do you interact with people without getting too personal, how do you be diplomatic, how do you give feedback, etc. More questions? Go ahead and unmute and say, Rudy, we still can't hear you if you're saying questions. I'm sorry.
Rudy may not have his mic on.
No, he says it's unmuted.
A minute ago, it was unmuted, yeah. If he wants to send it to the chat, if you can read the chat, then let me know.
He's muted now.
Oh, there is something in the chat.
At some time, Rudy's been unmuted and sometime he's muted, but he's unmuted now, but I still can't hear you.
Okay.
Okay.
Well, Rudy asked, what can you tell us about Krusny? Krusny, which has a 25. Are you talking about Krusny that has a horseshoe orbit? That asteroid? It has an orbit that is a little bit ahead of or behind the Earth. I can't remember which way it is. And it orbits kind of almost synchronously with the Earth. Yeah. Alan Hurd says, have you analyzed the light curve for Oumuamua? For what's your opinion? I have not personally. I've seen light curves from it. It is an extremely elongated object. I actually use some of the light curves as example activities in class for Oumuamua. Oumuamua was the first international asteroid that we ever saw pass through the solar system. Interstellar. It came from outside our solar system and passed through our solar system very quickly. And yeah, it's extremely elongated. It has a length to width ratio of like 10 to 1 or something because it has very high amplitude light curve. It might have been tumbling, although that might have been our view of the pole because the maximum and minima shifted over time a bit, but it may have been our point of view. Other questions?
You commented on asteroids
Yes.
as being a resource material possible.
Oh, yes.
But my understanding is it's a resource for orbital objects, activities, not for
Probably,
Earth.
yes. But if we are going to go into space and build things in orbit,
Right.
maybe build things that we want to take other places, even on the moon potentially, yes, it would be more, we wouldn't want to be bringing it back to the surface of the Earth. No. Yeah.
It's not a mining operation
Yes,
for
yes.
minerals or diamonds or anything. It's not a,
The big thing that people like to say is how much platinum and gold are in some of these asteroids. And it's, of course, hugely wealthy, but you wouldn't want to have to transport that mass anywhere.
hey,
Yeah.
you could make wires out of it for the
Yeah.
working
Yes,
on the
for
moon.
Yep.
Gold wires, that would be great.
Okay. Are there any other questions? Oh, yeah, Ted, sorry, go ahead.
Just to again make contact with the present time, when you talked about the Gen Ed program, one of the goals was diversity. Has the university been forced to dial that back in the present political?
No, I mean, that's something that we could not change easily because, wow. I'm also an undergraduate advisor, so I know about things like the requirements for degrees and et cetera. And yeah, no, there has not been any comment about that. I understand what you're saying about the political climate, but that would be affecting students over periods of years. You can't just change their degree requirements on a whim. So yeah, that has no change. That is all based through the state of Maryland. Since we are public university, University of Maryland, that's all from Maryland legislature essentially, and then the university senate. Yeah, so that's not a federal thing. Yeah,
What a relief.
yes. All right, more questions?
Well-
Yeah, go ahead.
No, I mean, I just thank our speaker.
Okay,
Thank
yes,
you all.
yes, thank you very much.
Thank you, glad to be here.
Yes, and well, what can I say? Come again.
No, wonderful talk. I'm
Okay.
very interested in how the students reacted to that.
Oh, yes, well, we can
That is
talk more.
very
Yeah.
interesting. So,
Well, thank you all. Do I close the Zoom? Do you guys close the Zoom? Yeah, what are we doing?
I think Flash will close it. He usually.
Oh, okay, yes.
I'm going to stop
Thank
the
you,
recording
everyone.
here.
Okay.